is putting use-inspiredness to it. So I always say, this is not science and technology to practice. This is bidirectional. We actually learn a lot from the problems and the users. So it's also practice to science and technology. So we take requirements and learn from those requirements and how advanced techniques can be applicable to those problems. But this requires a lot of collaboration, not just with our kind, but at the cross-sector, cross-disciplinary level. And our tools need to reflect on that. We have some, I think, virtual challenges to be with. It's okay. Not sure if I should wait. Okay, perfect. Be heard. I need to move the mouse back. Got it. So what I was saying is our systems should enable this collaborative thinking and collaborative teams. So how do we do this? It's one of the problems. The second is, I think our keynote speaker this morning did a really good job talking about IoT and applications of it and the challenges of it. We are in the age of big data, IoT, and AI. And in scientific computing, we apply that also to modeling and simulation. So we hear a lot about closing the loop between different parts of the scientific process. This is really taking the data, making it useful through AI and knowledge systems for that application, and as fast as that application requires. Sometimes data comes from sensors and ubiquitous systems. That's the Internet of Things that could be applied to it. But overall, when we talk about data, we are talking about capacity and capability to process that data. So let's focus on the capability part of it. We have big data systems that we need to apply for different types of data. So these are these polystore systems, and they distill different challenges of big data on volume, variety, velocity, you name it, and generate value out of that as fast and scalable as possible. And then we have different accelerators now, or processing unit, GPUs, TPUs, many different types of processing units, different accelerators, chips like, and architectures like FPGAs, field programmable gate arrays, and edge computing systems. So these are different capabilities that could be useful in the context of IoT and AI. But they are capability oriented, and those are part of building blocks for solutions. And overall, we also have the same high performance computing challenges as parts of these applications. So how do we combine capability and capacity as seamless as possible in the context of applications? So the workflows come here, and workflow thinking comes here quite effectively. This is actually a recent report that we published as a study group at the National Academy of Sciences. It was just released last week. We introduced it. So I recommend skimming through it if you're interested in applications. It has some good challenges and also example applications of this kind in it. And it's about advanced research workflows. So thinking in workflows, first of all, helps us move the AI closest to that solution and to integrate it into applications at each part of it. And also, it helps us to work as a team on different parts of the problem and integrate our work into a solution. It also gives us a way to be more fair, findable, accessible, interpretable, reusable, and responsible about these techniques. We can actually decide on the relationships between different services and how we are going to integrate them together, put some contracts and things like that at the interfaces that these services are coming together. But this all integrates with computing and requires that continuous integration of computing in dynamic workflows or as a dynamic systems capacity. So then something to take away is systems also should enable seamless integration of AI into applications as a part of workflows. And these could be workflows in a formal way, workflows that come together in different solutions as within architectures. Third, related to it, we live in a many systems world. I just put some recent news from HPC Wire. Just go in there and look for those news, but just to give a few. The first one is 5 new XSEED allocated. XSEED is our integrated collaborative environment to have systems available to researchers. One of these is on high performance cloud computing, and 4 of them are new architectures for doing AI. So these are systems, machines, sitting there as a capacity to do some AI functions. And how do I take something running on that system and integrate it with the rest of the HPC becomes a problem. These two are, one is at TAC, Texas Advanced Computing Center, one at the Supercomputer Center, adding software-driven composability features to existing supercomputer systems. And this one is about AI at the edge, edge-driven future, an interview by Pete Beckman. So when you look at these, they point us to a direction. These are many systems, and they help us with data and AI integration. They help us with having access to heterogeneous system. And they also help us or make us think about collaboration. How do I work with these systems, collaborate with them, because they are not the type of systems I work with. And existing systems then are at the moment even, data is not just storage anymore, it's knowledge systems, data management. We are talking about in these systems a continuum of distributed computing, edge, cloud, HPC, everything in between, networked computing, and high-speed connectivity. So distributed computing, but with higher speeds and with actually software-defined functionality that we can program these networks. And as we look into the applications and how applications are developing needs for these systems, we are thinking of interoperability of these systems, dynamic scalability across these systems, on-demand interactive access when we have a lot of data within the cycle. And when we use these different systems, we need to think of performance measurements because we are talking about dynamic capabilities and provisioning. And also at the face of the services that we are integrating into these applications, composability. So then we need to think of these now as an ecosystem, right? And a strategic ecosystem that's capability oriented, that's for capability integration. And this could come in the context of services or integrated solutions. But reuse is in the heart of this because we can have those services built for one purpose. In some cases we have to, of course that's the nature of things, but most often than not, we need to have reusable services on these systems so more applications can make use of that. Really ambitious goals we have ahead of us in that sense as a community. And when we typically integrate those into applications, as we are talking about, people coming together with some problem to solve, with some data at their discretion, and management of that data, turning those into insights, including them in modeling and simulation on top of systems is the activity. And what makes it turn, of course, I mentioned workflows before. From my point of view, it's a part of a workflow, but it's not just a workflow, it's team flow. It's a collaborative team applying a methodology so they can actually create a solution together. And once we have that, we will make that useful in the context of dashboards and things like that to not just HPC users, computing users, or scientists, but also people who can take advantage of the findings from there. Like in COVID-19, how did we make things useful for decision support? We had a lot to learn, right? We weren't ready. So we need to integrate. And I'm going to talk about 3 things about integration. 1, dynamic composability. We need to be able to, at some point, compose these systems dynamically so we can use them effectively. The second thing I'll talk about is systems and services. I talked about systems and services, but how are we going to make them integratable into applications? What is that application integration layer and what do we need there? And then third is very important, and it's not something we often talk about. Tools need to enhance teamwork, and also they need to use practices or principles that encourage responsible AI practices not just responsible AI, overall in our end, responsible science practices or application integration practices. How do we make something dynamically composable, or what do we mean by that? There are systems, hardware, software, network, storage. There is a resource management layer on top of that, and there are services that run on top of that. So this is both containerization at the hardware and software level to make things integrate. The second one, how do we integrate things? Again, I use workflow management as an application workflow, not a formal workflow, although it could be a formal workflow, but it could be just a notebook as well. There needs to be some layer for application integration, coordination, optimization. These are all part of it. But when we do that at each level, we need to think of data lifecycle management. This is not just storage, or even if it's storage, it's active storage, passive storage. Those are all the decisions at different parts and phases of the development, but also reuse and services, and how does data become knowledge? So all of these layers can reach data, and even the performance-related knowledge. How do we take performance data and turn it into insights so we can steer our systems? We can use it to map services. We can use it to integrate services. And the third one is this blue part, right? How do we make people use what we do? How do we create a team that can actually come up with that solution? How do we make it reproducible? And how do we make it responsible in terms of fairness, accuracy, explainability, ethics? All those things need to be a part of our thinking. Once we have that, we actually come up with this tree and very complicated diagram. And we need to now go back to this diagram and say, okay, we have a solution to be had. How do we do every part of it? So it becomes sort of a reference architecture for these solutions. To turn this diagram to be a little simpler in the context of what I'm going to talk about, definitely there's that use-inspired solutions. But what we are talking about is having, from a computing perspective, compute storage network, some composition and API layer to it, and having services and applications that can use that API. There are some principles to play in this space. Dynamic measurement, management, and provisioning is very important. Creating plug-and play microservices that we can actually integrate into applications is another. Being able to run those services across many systems that can be a capability for running these services is another part of it. And making sure things are fair at all parts of it. So it improves actually reuse, interoperability between systems and services. So these are really things that we talk about when we talk about these solutions. So what are some composable systems? Expanse is our latest supercomputer at the San Diego Supercomputer Center. It's not just a composable system, it's a full-blown supercomputer. But it has some innovative capacity. It has, for instance, cloud bursting to commercial clouds through Slurm, or it has a gateway that many people from different communities can access through. And as a part of it, what we also started experimenting with is this composable systems functionality. So this is not Slurm anymore. We are actually reserving a part of this computer to be a Kubernetes cluster. So we have some nodes that become a Kubernetes resource. That's sort of a pool of nodes. And that's something we are working on as we have more demand, dynamically scale between Slurm and Kubernetes parts of the architecture, and it's in the works. But Bright Computing has a plugin called CM Scale that will help us to implement that when it's ready. Other computing platform, starting with the network, is the Pacific Research Platform. Pacific Research Platform in 2015 was a vision to connect UC campuses through the California's education network, CNIC, at 10 to 100 gigabit capacity. Once that was achieved, And these flash I/O appliances with 8 gaming GPU nodes, now any type of architecture actually, including neuromorphic capability and a few other things, can be added to it. But at its heart, it's flash-based I/O nodes that we called Fionas on top of a network. And then we took PRP and added GPUs across that network to turn it into a Kubernetes cluster of resources. So once this was done, more is coming. Over the next couple of years, the idea is to add more GPU and storage across the USA, not just through California. So when we look at all of this, it's actually more than petabytes, actually 4 petabytes of storage available through this and many GPU nodes. But since Ceph and Kubernetes and other types of things were added to it, it's a cloud compatible, so we can actually integrate any commercial cloud type of data lake functionality or other storage scalability through the integration of those, pooling further. So when you look at PRP, it's a small resource. It started, and we call it sometimes potluck supercomputing. You bring your own GPUs or resource and you get more from that. Who doesn't eat more in the potlucks than what they brought, right? But joking aside, it's now has close to 8,000 GPUs, CPUs, sorry, and close to 600 GPUs, close to 4,000 terabytes of storage, and 600 different namespaces. That means 600 different projects and individuals using it. As an experimental resource, computer scientists mainly was the target, but over time it became quite useful to many different disciplines. So what we've done, since the Kubernetes clusters are the basis for both expanses, enthalpy is the part of expanse that we refer to as our Kubernetes cluster. We used Admiralty to federate the Nautilus, which was done by PRP and Chase CI, with the enthalpy. So we can now federate those as a pool and distribute applications and microservices running through these two resources. And I'll show you an application of that. Another thing that was done in Chase CI is to start pushing some of these nodes to wireless networks across the county. HPRN, High Performance Research and Education Network, is in the back county of San Diego. Was funded by NSF back in 2000, and it grew from there. It has weather stations, it has camera nodes, it has geophysics type of sensors. It's a sensing environment, or observatory environment. It's a typical one with combined with networking. So some experiments are done to push different types of accelerators to the edge of HPRN just for static capability of being able to run AI-based inference code at the edge. But think of this, this was one service running at the edge of a network. There's no scheduling involved. We had to know what we are executing. It was experimental. What I'm going to talk about next took that to the next level. So this is a project led by Pete Beckman at Argonne National Lab in Northwestern. And here are some of our team members. What Sage has done is take the edge concepts, and Waggles are the nodes that the team at Argonne built over time. These are sensing units coupled with AI accelerators. So they are an environment, a small environment to do inference or federated work, learning or things like that in the long term. So the SAGE project added these accelerators into the networks funded by the National Science Foundation. So we are still deploying in experimental capacity. NEON, Ecological Observatory Network, HPRN again, a few others here are listed. These were existing sensor networks. So now think of adding what we refer to as wild SAGEs, which is the small devices with accelerators out in the field, and also SAGE blades closer to where these nodes come together to power. So a little bit more advanced nodes, so they can also have some capacity in storing data, doing stream processing and things like that. So that's the architecture. And when we think about it, there are some sensors, facilities, actuators, right? And edge computing happens closer to that. But then there is how the rest of it happens. Now, this is an environment now. We are talking about multi-tenancy. Users will come to the Sage portal, and they'll request access to these edge nodes, and they'll be able to schedule their AI inference codes on top of those sensing units in the accelerators. Scheduling is a problem, and it's a different type of challenge than we have because these are small environments. Prioritization requirements on the urgent scale become important. How does that AI come to being? What is it that trains it? So on the cloud end, there is definitely other types of computing, but there's the virtual Sage that users can come in and use the data to generate their AI containers. And they become, not just data becomes available, but those containers become a part of edge code repository ready to be deployed on these edge nodes. So it's an interesting environment, and the capacity is growing there. Talking about composability, what we have done is we integrated Expanse, Nautilus, and Sage. And for development of those AIs, we added a Jupyter Hub on top of that. Jupyter is, as you know, these notebooks, and the hub can have, it decouples the programming part from the backend, the kernel. So you could have actually across a set of distributed environments also. So Expanse and Nautilus have the K8s, which is the real Kubernetes, and K3s, which is the lightweight Kubernetes, was applied in Sage to turn that also into a cluster we can combine with these resources. Then users then come here, ask for the type of nodes they need access to, and create a cluster that they can have multiple executables or microservices running on these different nodes. So if there are different AI nodes available, for instance, they can couple those together and create a pool of these things that they can use through their notebook. How does it get applied in the application scale? Let's talk a little bit about that. And over time, something that surprised me is I've become known as a FIRE researcher. And over the last 15 years or so, I've been working on applications on FIRE modeling, but not the FIRE modeling part. It's to enhance that FIRE modeling through big data, IoT, and computing. And later on, of course, we started calling things AI, and through AI these days. FIRE is a big problem. I don't think this is a debate anymore. But FIRE is good. Nature needs fire. It's a natural process. But the mega fires, the way we are having, aren't good. So if you have time over the break, I'd be more than happy to talk to you about what is causing the fires we have. But today I'm skipping that. Don't talk about that in Sicily. Okay. Don't say Bruno. So real-time operational use is one use of fire modeling, and also understanding fire physics and building mitigation preparedness systems based on what we think these fires will look like is another part of it. These are different time scales, but what you need to know is if you know about weather, fuel, and environment, landscape, topography, for instance, you can model these fires with different techniques. Some of them are more computationally intensive, some of them are less. And today, we have next generation fire models that actually can take advantage of data, really detailed data from different resources. For instance, weather forecast is getting more detailed. We have more access to satellite data, weather station data, camera data that could see the fires or the landscape, LiDAR sensing, remote sensing, as I mentioned, from satellites about the fire or the fire environment before and after. We can have overhead sensing through drones, firecraft. Fire perimeter, for instance, is something now we are getting used to measuring in California on a real-time basis through planes. And, fuels, which is the vegetation that burns, and there's a huge buildup of it, but it changes over time. It's a dynamic environment. The other thing that I'm going to talk about is there are different models, as I mentioned. If you're just doing fire response, you're pretty good because there's real-time data. We can learn about the dynamics of that fire as it's happening through that data. And you can get away with a less detailed model that runs fast because fast is your objective, not super accurate. Accuracy can come over time by adjustment of that model through AI. But as you go towards this end, like planning communities, doing fuel treatments and optimizing them, what's the best place, where and when to do these? Ecosystem sustainability decisions, how will climate affect fire behavior? These type of things, they're becoming a lot more complex and detailed. And the requirements are detailed. Their complexity in terms of computational complexity and need for detailed data is also a lot more different than real-time response. So this is what we do in the Wi-Fi lab. We try to find the ways of linking the right data and computing at the right time to fire science and make it useful in the context of applications and solutions. Solutions, FireMap is for initial attack fire response. And it's being useful in operational context in California, both through the Governor's Office of Emergency Services and CAL FIRE to date. Wi-Fi Edge is how to deploy AIs and what's the architecture of bringing the data together with edge computing. Burn for 3D is for prescribed fire optimization, which requires different type of fire modeling. So all these three, actually, different types of modeling for AI and fire science. And remember, I talked about collaborative environments and making transparency in the environment. They're all powered by that same environment that makes data and computing and models and a gateway that can do AI available to the science. So Wi-Fi Commons has multiple layers. Data Commons is where data gets cataloged and becomes available through APIs through a federation. We don't store a lot of data. We federate it. We store, of course, the value added to that data. But it's really through data agreements and federation of data from different providers. Model Commons is when we have AI models, containers, fire science models that we are running and turned into microservices that can run across these composable systems. That's where they get published. And there is a knowledge system and an ontology that connects these so we can actually map workflows to data and integration. We can do some smart things there. In the middle, what you're seeing is the Jupyter Hub that I was mentioning before across that three systems. So that becomes available to this community, along with other communities I'll talk about, through the AI Gateway. And, you know, this is actually the external facing part of it, right? The users, who is going to use data to generate models, and how will they publish those models? So there's some usability for right now the expert user in that case, that can make these models useful or curate the data for fire science. So I'm going to talk about two ways that these type of AI systems are enabling, or these composable systems are enabling, reactive and proactive. Reactive is by so over the last decades, we created through an NSF program this FireMap tool. Initially, it was an infrastructure that brings data to computing and fire science, and our goal was to demonstrate dynamic data-driven fire modeling. But then LA Fire Chief called me and said, how can we use it? We went there. We have middleware workflows. It was 2015. And we are sort of looking at each other to understand their requirements. So together, we developed FireMap, which was for initial attack, because in LA, when a fire ignites, for that fire on the right day to hit the ocean, you have 2 hours. So initial attack, the first couple of minutes of that fire and starting the management right then is very important. So then understanding the ignition, where it is, where the fire will go becomes a huge problem. This then got adapted by California, and now we have planes flying, and we run a fusion center 24/7 for the state. So this become quite effective and useful that way. But again, that use inspiredness instilled into it by LA Fire Department made the rest of it possible. So it wasn't us telling, oh, the interface should be like this, or I need models at this time. And what is the AI in it, or what's the workflow in it? So it's about characterizing the dynamic fire environment, the ignitions, variation of wind, smoke, moisture changes, fuels, perimeter evolutions, and detection of those ignitions is how it starts. And then you start collecting fire imagery. But the moment an ignition happens, which can be at the edge, I'll talk about a little bit, it becomes available to fire modeling. And it gets combined also with other things that combine better, for instance, or fire perimeter, and do the adjustments to assimilate that data into these models. Let's talk about smoke detection. How does it come to being? It's a research area on its own. A lot of people are trying to crack this nut as we speak. Right? But you need a system architecture that can bring data in the first place to these different experimental AIs. But nobody had the labeled data. So what we've done was first work with fire experts to label images so we can publish this training data to the community to develop AI models on top of that. So there's an enablement component, that transparency of the training data component, and collaborative development. Many people can have different services that do this, and who wins in the end? We can generate ensembles of these, and the community wins. So that's one part of it, but once you have that, how are you going to run them? Edge and composable systems, the systems that I talked about before, becomes important there. And we have these camera networks, having the edge systems deployed on that so we can run these closer to the cameras was the other part of it. When we look at that workflow right now, how that happens, on Sage, there's a smoke detection workflow that triggers a fire modeling workflow that gets on Expanse and Nautilus. And there's also at the same time, over time, I should say, not at the same time, as you have more data and more ignitions confirmed by the Fusion Center we have now, we can retrain these workflows. And that's, again, training and inference becomes a part of the knowledge growth over time. So let's focus for a few minutes on prescribed burns. Whatever I told you, throw it away. It's not going to work. Because prescribed burns is about detail. And 2D, where the fire will be at what time, at 30-meter resolution, no, it's not going to be enough anymore. So fast 3D is our goal here, because 3D models until now, they take days to execute. Instead, my colleague Rod Lynn at Los Alamos National Lab, he did a reduced model that can run faster, but still have those processes built into it at the fire behavior level, called QuickFire. And we also work with US Forest Service, I'll talk about, on 3D inputs to these models. Why is this important? We have a fire deficit. It's a little counterintuitive. In the US, we have too little fire, too little good fire, too much bad fire, which becomes a mega fire under the right conditions. We suppress all the good fires that nature needs and cleans itself through. So along with many other problems, this is one of the problems that causes that deficit and fuel accumulation. So on the right day, a little spark turns into this big thing that takes off. So one of the strategies that was introduced in the infrastructure bill this year was ramping up these prescribed burns by 4 times at the national scale. In California, the strategy is the million-acre strategy, which is 10 times. But it's not easy because these are really risky to execute. If you heard about the New Mexico fires last week, and it's still ongoing, it's a prescribed fire gone wrong. So what we are trying to do is to optimize the planning of prescribed burns so we can increase weather windows through optimization of where and when to burn in the first place. And for that, we need models like this. See if I can make this work. We have 3D fuels going into, maybe it's not that visible, but there's like, it's not a wildfire. It's not torching through the environment, but it's showing us, it cleans some things, leaves some things behind at that point. So what it does is, this was our response mode, 30-meter resolution 3D, and it gives us in half an hour steps where the fire will be, its direction. And this one is 3D through QuickFire. And it can account for 1 meter scale weather, fuel, ignition pattern information under different, because prescribed fire is literally putting fire on the ground to burn and clean an environment. So then before we do that, it would be really good to know its behavior. How is that going to behave in an environment? What it's going to take away, consume as fuels from that environment. And if we know about what it's taking away, what kind of emissions it turns into, and how that smoke with those emissions transport and which communities it hits. That's a more complicated problem. And when we talk to the communities about this, we were told they don't have high resolution 3D dynamic fire environment data or any environment data that way that could be coupled to these models. And the speed, flexibility, and interpretability of these new next generation fire models is pretty low. So the first thing we've done is to make that speed a little better. So we can actually, through an API, across the systems I was talking about before, Nautilus and Expanse, but also through commercial cloud providers, we can scale the execution, and we can run many of them at once and give the community a little bit an easy way of running these models so they can run many ensembles of these. So that was the microservice component, right? And what we do now, before anybody plans any of these prescribed burns, they run many of these ensembles with different conditions, and they can rerun them if they wanted. And we give them AI-based interfaces to allow for analysis of these. So there are a lot of things in the background that helps us how risky they are, if it meets the objectives, and what kind of weather windows they have to match and prescribe, because prescribed fire means there's a prescription on how and when, what kind of weather conditions to burn it. So we help them generate better prescriptions that allow them burn on more days, hopefully, if the weather allows. But so there's a lot of background AI to these interfaces that way, but there's a user experience component that's translated through community interactions. We have think tanks with the community. Another thing we've done is what kind of better data can we give them? Fuels, 2D, 30 meters. Now we are able to actually generate them in 1 meter resolution. So it's like 900 times more detailed in 2D even, but they have this component that's a 3D. And each of these voxels, those little cubes, have density, burnability, moisture, and other characteristics. And we generated for the continental US once. It took us 6 months, by the way. But now, every time LiDAR information becomes available, we automatically, through workflows, on-ramp them. And in that workflow, you can imagine there's a lot of AI ML going on. It's someone's job to do these on-ramps, right? Both from terrestrial and aerial on-ramps. So for Yosemite, for instance, when we have that terrestrial on-ramp, we know this is how the trees are. And this is one of the 900 scenarios, right? And this will be how it's going to look like. Which of those trees will be still smoldering or charred when they are done at the end of that burn? And, you know, is that burn a ring ignition, a straight ignition, aerial ignition? Those type of decisions can be made through these models. And on top of that, once we run these models on the day off, I don't want to rerun. I don't want anyone to run models. So we are combining physics-guided machine learning principles to generate emulators that can then, on the day off, be used on a fast scale to reassess the risk and make a go, no-go decision. And at the same time, we are looking at wildfire risk models and combining it with these, so we can have regional scale where would be the most impactful to do the prescribed burn in the first place. So this type of trade-off optimization decisions are important, but explainability, right? Why something, why is a risk a risk? What kind of model put that together, and why is a part of this interface for burn managers or fire planners that are working on these models. So explainability at the scientific scale and at the decision support scale are very important parts of it. So the day off, we have, let's say, high resolution data, or we have these models and we are burning, but how do we make sure we know what we are doing at the day off, or afterwards, how do we evaluate how it worked? So we are using high-resolution data we are starting to use from SAGE. This is an example that happened last couple of weeks. So these SAGE deployments are deployed with the right type of sensors in it for, cameras, smoke, and weather and humidity, and many other little sensors in there. And before, this is a mobile processing unit from Neon, and it's the Kanza site, a research site in Kanza. Before, running ensembles models of the environment, deciding on a burn prescription, and making sure we have that mobile unit that senses the edge unit can be brought there is important. On the day of sensing the environment, making go, no-go decisions, deploying edge codes, for instance, smoke detection was tried in that recent one, and setting up a SAGE dashboard and operational room, actually they call that the war room, to actually manage what's going on. And then afterwards, publishing this data in Wi-Fi Commons so others can take advantage of it, but at the same time, conducting post-fire evaluation and creating adaptive prescriptions. Did it work? And how do we reflect what we learn into the future prescriptions of that area? Again, Wi-Fi Commons enables a lot of this. In the back end, fire science is a part of it, and the environments that we can actually use that fire science in a use-inspired fashion is other part of it. So I have about 5 minutes, and I'll talk about a few other applications, because this is actually pretty repeatable, turns out. The first applications is in neuroscience for volumetric electron microscopy imaging and finding regions of interest in that. And to do something like this, you need to train AIs that can infer from the imagery to do the task at hand. And same approach was applied at that level. Expanse was used for training and simulation, and that also breaks that cycle of measurement and simulation here. And inference was deployed, in this case, NRP, which is that National Research Platform, which is the expanded PRP across the US. And again, there's a simulation pipeline that runs on Expanse. There's the modeling pipeline. I simplified it here. Inference, training, inference, right? And there's a Ceph-based storage that connects and federates the storage behind these different systems. That's actually the dirty secret of that. There's a storage federation, and that part is a pretty difficult problem to solve right now because Kubernetes is not actually meant for this type of thing. I think we are pushing the boundaries there. So I don't definitely suggest it as the solution, but that's what we're experimenting with in composability. The other was an example from the COVID-19, and I think COVID-19 taught us a lot as a society, but one of the things was how do we increase trust in science? How do we increase use of the scientific knowledge generated, not 10 years later, today? How do we build systems so as understanding grows, we can make it a part of the decision support? And there were many types of data, right? Disease data, virus models produced, even molecular atom-to-atom interactions, wearables, public health surveys. There are so many different models at different levels, not just for understanding the disease itself, but also its effects on the society in terms of mental health, economical impact, you name it, in the business life. So how could we make sense of all this data? I think we have a lot to do, but going forward, if we can make sense of or harness these data sets really fast, we can use it for decision support, for policy making, vaccine, treatment, cure, like many different uses for that. I think we would all agree on that. The one that I was involved in a study is at the personal scale. These rings, Aura rings, you might have heard of them. They're medical grade sensors, and they collect physiology data, including your sleep, heart rate variation, temperature, and things like that. So through UCSF and UCSD, Benjamin Smar is the UCSD professor who led this team of researchers. We were able to work with Aura and in Aura, the good responsible bit is you own your data. You can donate it to a study, and it's a very responsible company that way that, you know, if you're in control of what they do or what gets done with your medical or physiology data. 70,000 plus individuals donated their data, and there were public health surveys that hospitals, UCSF, collected from these individuals at the same time. So it's the biggest study of its kind to understand the disease at the personal scale. And the idea is we integrate data coming from these 70,000 plus IoT devices, little rings, right? And process that to generate alerts for these individuals because their physiology is changing. Make them take a survey and test, and, you know, continuously do this, right? Night after night. So it was a big challenge. 4 different data systems are involved in there. The data comes to Amazon, goes to a HIPAA compliant secure client. It gets anonymized, go to a timescale database. From that, goes to an environment that our AIs can make sense of it on Nautilus, that environment I was talking about. So once we have that, we also had partners making use and generating these analysis on top of them. How do we make the front end for that collaborative perspective? We have that user concept, of course, and a user environment, and we developed over time a methodology that I refer to as PPODS, process of practice of data science. So this is about that microservice integration and how things come together, how people collaborate and their expectations from each other. So we applied that to achieve that application integration step. But another composability at different level, right? And these are different applications. They are not turnkey. To summarize, and I left in my slides some pointers to the papers who describe these. I think these are emerging new applications. They all integrate AI into the process in a different way for it to be useful. By the way, in that Aura study, some individuals were alerted. They took COVID tests. They didn't know they had COVID. Their temperature rose like a little bit, but their whole integrated heart rate variation plus temperature and other things were so different than usual. The system knew they were asymptomatic positive, right? And we also have, in this case, so how vaccines affected different people at the individual scale. So it's interesting because all the models we know are at the societal scale, so it makes disease a multi-scale problem, right? At the individual scale, you know some things. And at the societal scale, can we model things differently next time with averaging different types of people and their patterns? And these are all complex applications. And I get it, we have a big team behind it, many experts, but I think these systems backend of composability and the type of systems we were able to integrate through services into this helps. And that's what I'm here to advocate for. Let's embrace that complexity if you're going to talk about AI. And let's work with data experts, computer experts, scientists, users all together to really distill that value that we are getting from AI in the context of the applications at the scientific and societal scale. And when you do that, it becomes really an interesting educational opportunity for student training as well. That's for another talk. And I also want to acknowledge that this comes at a cost. We are not going to have turnkey. We'll have more human-in-the-loop processes here, and will require a different way of thinking these end-to-end pipelines, and it's going to require a lot of collaboration with infrastructure providers just to make that storage backend. You know, things had to happen. So I'm going to leave it there and open it up for questions. Thanks for listening.
Okay, many thanks. Okay, it was very interesting. Okay, I stay here. Okay, it was very interesting from my point of view because, of course, you talk about, innovative technologies and approaches, but most of all, it's very interesting to understand how to apply them and the value of our work, our research, and the importance of the collaboration among us and collecting all our activities. Thank you very much. Very interesting. Okay, there are any questions? Yes? Okay, thank you.
Oh, sure.
Great. Thank you very much for the talk. It's very interesting. When you talk about pushing AI and this kind of information out to the edge like that, one of the big things that comes up in my mind is interpretability. And so specifically to like the Aura Ring, you said we had people taking tests, we had people monitoring, and we found asymptomatic people that we used an external test to see that they were asymptomatic. And we think it was due to these, small correlations between different physiological effects. Have you been able to sort of address how do you bring what the AI model is seeing and making decision back to the user? Or did that require a lot of data mining after the fact to understand that? And how do you make that more accessible going forward?
Yeah, so that's why I started with use-inspired and making sure the users are in the loop. In this case, the user of that insight is the doctor at UCSF. It doesn't go straight into an individual for an alert. There's some medical expertise there. And so that was handled through that, initially the interpretation, because we knew it's not like a direct scare to a person. But right now, there's a huge team of students. MIT Lincoln Lab is involved, for instance, in really explaining those insights and maybe turning that into some more, like there are a number of papers being written. So that's going to take some time, right? But if that data, if we didn't find a way to make it useful then, we would have lost the moment. That's the main thing. If it's the doctor who needs to get that and interpret it fast, and maybe if they don't get it right every time, maybe it's fine, because we still have a buffer of responsibility there. And over time, we can use that to be a learning of what the system has done. We've done a similar thing with the fire, right? We run a fusion center. We train modelers, and they model the fire, but we don't push it without fire managers. So fusion center has the modelers, who are the people on our end, but also managers who are firefighters who are going to evaluate it. We also use a number of data, right? From cameras, satellites, ignitions from like broadcasting. Even then, we make that really accurate ignition confirmation. And the model still waits until the manager approves for it to be pushed. And all this is done in 5 minutes. Like if it's after 5 minutes, we lost that initial attack window. And through that, the plane gets ordered. So over time, over the last 7 years, in essence, through initially LA, then Orange County, now at the state level, we were able to make that practical workflow right, and it's constantly being improved. But for instance, we don't use smoke detection in the fusion center until we are sure this AI will be useful. Just this year, over the next year, we added a component in there for the modelers to evaluate. So we have a firebot, for instance, that automatically models. None of that gets used in operational context, but it's there to try on the side and experiment and evaluate. So maybe over time, we can make it useful. We have less false positives, and maybe that helps. So we have students working on using different detections with the smoke detection to make it more accurate. There's never one type of information. And I think the more information we have, the more confidence we have in those insights, then they are ready to be pushed in a way that the users decide how. We don't get to change the user's workflow. Initially, we didn't actually. Now, the culture is so data-driven in that program we have that they listen. And, actually, these type of ideas are entertained because they are seeing the success. So the data culture is happening through use of it over time. Long answer.
Great question.
And I'm very grateful for your work on the fire detection as a fellow Californian here. My question is how we would reconcile the increasing size of the models that we generate in all the transformer models, who are huge, gigantic a set of parameters, with the move to the edge and the distribution of data, which is kind of often not as powerful to actually process it. You have any idea how you go after that?
So yeah, now we need to scale down. We talked about scaling up for so many years, and you know, I'm not an expert on that topic, so I should say it first and foremost. But inference is actually, like, these accelerators are quite capable. So inference is not, you know, a big deal, so to say. It depends on what we're inferring, of course, and the complexity there. But often we didn't find that it's a big problem with, especially when we have the Dell blades, not, you know, the real age wild sages in that case. But federated learning is also something that, you know, we heard throughout the day a lot about too. So I think more and more I'm seeing more like a binary ways of modeling things. You know, there are different techniques emerging there, but I think it's a huge challenge overall to think scaling down, because for years we assumed that it's always going to be more, and now, oh, maybe we can think small. And the data is small, frame rates change, so there are lots of advantages on the doability of it. And I think edge environments are also becoming a little bit more capable. So I think it's a no answer to your question, but this is our experience that I can talk to.
Okay, first of all, thank you for your presentation. It has been very interesting. My question is more related to workflow. I mean, I see that in the last years we started to work with serverless and function as a service, and I see a clear marriage between workflows and FAS, because in my mind FAS are building block or a workflow, and you showed in the last slide that, for example, a platform like Kubernetes are not ready for that. And for my small experience, I agree, because Kubernetes is more similar to our operating system for the cloud. And there are many platforms for FAS, like, for example, OpenFAS, Fission, and many other, that tried to do workflows, but they didn't manage. If you open GitHub and you search for OpenFAS workflow, there is a whole repository. Same for Fission, same for another platform, I don't remember the name. Same for OpenWhisk. OpenWhisk tries to do workflows, but they create only sequential workflow, and in my opinion, it's a very limited workflow. What do you think about this, about serverless and the marriage between serverless and workflow?
I think you're spot on. There is no single workflow system that can integrate it the way we are seeing to, you know, coordinating these. One thing that, you know, I worked on workflows earlier in the grid days, and, you know, I kept working on them, of course, but service integration was the concept, and those services themselves were quite capable initially. Workflow systems did a lot on top of that. I think the same thing is happening. You know, containerized services, microservice integration is what the workflows are doing right now. And if you're, you know, working on the area, there's a lot of challenges in now integrating those with performance measurements from the system, because systems are becoming, if they're not white box, gray box. They used to be black boxes, right? You had the queue, and, you know, you had the guesstimate in a way. So that's one. The other is, I think, as we provision more and map to these resources, we can be a lot more effective about having the right pool. So the workflow actually almost looks like it's self-executing, right? At that point, that intelligence can be a part of it. And we tried something I didn't introduce today a couple of years ago. We sort of tried to do a suite that we called smart flows to categorize groups of executables, microservices based on their needs for applications. And, if you're doing exascale, it's one thing, right? There is a different way of doing it. If you're doing at this serverless level, it's another thing. I think we need to start understanding how we define performance at the microservice level, even if it's serverless, and have the right pool so that when we deploy that workflow, it's deployed on the right type of mapping and capabilities, so it becomes a service integration problem. Right? That's, I think, our challenge for the next maybe decade.
Thank you. And I'm sorry, but I have a second question. We are talking about continuum. So we have this environment where we have edge, we have cloud, and we manage to move data, but I'm not sure that we are moving computation. For example, you showed an architecture where we have two Kubernetes, if I understood well, where we have a K3S and another cloud-based platform. And do you think that is this continuum? Why we don't realize a single Kubernetes where we manage to use edge devices like Raspberry, ARM architecture, and cloud architecture in a single homogeneous environment, like in the osmotic computing, as Professor Rajiv said this morning? And I finish with this question.
So it's actually the answer to this a little bit linked to your first question, because I think we made our workflows too centralized over time. We made them too powerful and too in charge. This calls for a distributed management and leaving things be with the right type of intelligence and management built into it. And when we finally are able to do that, this is one approach, right? I think we'll be able to then have less homogeneity and more heterogeneity in the approaches. But there's also the data backend. And I think that's the missing sort of component, right? A lot of people are trying to have data resources that are close to these distributed resources and networks that are capable of doing something closer to the data. So I think we'll write the integration differently at that point. Once that happens, there's another step there, and that's going to make the performance a lot like it. It's also a bit counterintuitive, because if you have more steps, it should take a longer time. But maybe if you have more steps, it will take less time because it's done at the right place at the right time.
Thank you.
Thank you.
I know. Right to serve everyone.
I like it. Thank you for the question.
Yes, so my question is, what's the benefit of deploying your algorithms on the edge in this particular scenario? Probably digital smoke alarms could be a better way of doing it, because you just want is that from where the fire is coming and then consolidating.
Bandwidth, that's a big problem. So Sage, I can talk about Sage, has larger nodes close to the edge. And, it can take care of a little bit of the bandwidth challenge if a larger node is required or something needs to be done, or the storage to a point at that node, right? That's the limit. There's a limit to it, but that's one way of helping with that challenge. Did I understand the question right?
No, so what I'm suggesting is that if you have a digital smoke alarm that just detects the smoke and sends the signals, it does not need a lot of computation power.
Oh, it doesn't. It's just one signal going back and it gets registered.
Yeah.
And at the same time, okay, now I understand it better. That actually gets saved on a blade node. Like there's a Kafka server there, and it handles the stream processing and sending that data as well at the right time. But it's this choice between, if you have an alert or an insight that you need to communicate, do that first, and data slowly transfer, or do something with it, and transfer a version of it if there's a privacy requirement, for instance, that's related to that. Right?
Yeah, because you would require hundreds of sensors, and sending those kind of data sets of samples to a data center would be quite compute intensive.
It takes time.
Yeah, whether just 1 or 0 from a sensor, smoke alarm, coming to data centers, you could easily map on that where the fire is coming from.
Yeah.
And then probably you could set things in motion. that
Yeah.
would be a low-cost solution. That's just a suggestion, or
That's the current, yeah.
Yeah.
That's the current solution, actually, to send that, and that becomes an alert and gets written. And over time, the rest of it becomes available as a training data. Does it work in all scenarios? Probably there are parts that will break it because maybe that insight needs to come with like a frame, right? That might be a little longer, but it's still not a lot.
Thanks for your talk. When I listen to you, I have the feeling of an unlimited deployment of infrastructures, hardware, infrastructure, software. And you know, we are in the age where the energy price increase a lot. We know more and more the environmental impact of ICT. ICT is not very sustainable. So do you take these metrics of energy efficiency, sustainability in your platforms, in the future development of your platforms, or do you think that the end justifies the means?
So sustainability and the energy efficiency of these. In my opinion, these are more energy efficient than the general computing, and I'll explain why. The long answer is, I think the first part of your question was endless resources. We kind of think endless within the capacity, right? And, you know, of course, there are things that we need to do at times to ensure things run right, or, you know, we add a further pool. That's why the cloud, you know, over bursting part helps. Coming back to the energy, for instance, that Burn Pro 3 API, the Quickfire API to it, it's done in a way that we only deploy the nodes we are going to use at the right moment. So instead of maintaining, you know, a cluster or a service, that instance that constantly is there, it gets deployed and pulled when it's used. That's why I think it's more energy efficient, because you don't have to keep things active all the time. And do we do that research? We don't personally do that research, but if anyone is interested in that, we'd be happy to work with you on that. Not our area.
Thanks for the talk. So I had a more basic question concerning the word composability that you used. And so what makes the system that you have used or built composable in the way that what is the provided architecture, like system architecture, design, and maybe even implementation?
Yeah, so in this case, composability is the dynamic pooling of resources at hardware and software containers and the management of that, right? And what makes it in this case is we use Kubernetes and the ecosystem of tools in there, which helps Ceph is the storage, for instance, and things like that I mentioned here and there in my talk and slides. In that sense, do we call it composability or the continuum computing? You know, those are definitely, but the current name for it at the industry is, you know, these capability-driven services and integration of systems out of those. That's composability. And that capability includes where and when things are running and how they integrate. For instance, these solution architectures for some composable digital blocks or infrastructure has the concept of periodic table. So you'd see, it's very common these days to see a periodic table with different colors for different functions. Like there's the data part, there's the AI part, there's the integration part, and you know, you pick and choose from them, and the backend microservices and pooling happens through the middleware layer. So that's what's called composability. And I mentioned also, you know, interactive use and a few other things in my talk. That's what I mean by.
All right, okay. I see your perspective, at least on composability. I had one more question, just a rebound on what Laurent just said concerning the energy. Concerning, for example, the scientific observatories like NEON and stuff like that, how can you just deploy when it's needed, when it's a continuous observation of the environment that doesn't, I mean, it's not coherent with what they are doing, at least?
So how can you deploy when it's needed? In this case, the deployment is a mobile unit. You need to bring the unit there to deploy it. And most of the time, these networks also have fixed nodes. And the Wago units in Sage is deployed on those nodes. And networking is there, data infrastructure and things like that are there through Neon, HPRN, and other places. But Sage also connects to its own sensors and creates a repository of those. And it makes an interesting model because you can't just have fixed edge devices. But for wildfires, in wildfire mode, we have those on camera nodes, an alert wildfire, and they keep watching, right? That's one way of doing it. In this case, the example was, that's why I gave this example actually. It was a prescribed burn. So you change the location of those. And with that, the deployment also moves. And so you could have these temporary edge capability added to the rest of it through it. I think we are out of time. I'm getting the sense.
Okay. Sorry, but I mean, the topic is very interesting. Okay. Before closing, yes, please give us the opportunity to say you thank you. So, DK, please, can you come here?
Appreciation for your valuable speech at the 22nd ticket.
I have to thank you, Kai. I will just small announcement. Something we have to do during the gala dinner, but now our special guest is leaving tomorrow. I want to say Omer to come here to give you a plate of appreciation. Maria, please also give him, because we know you go tomorrow and all the time you are busy. And thank you, Omer, for everything. Thank you. Okay, and it's time to break. We are 20 minutes later, and I suggest to make some announcement.
Okay, please, there is the poster station downstairs. So you can use this break also to give a look to posters and to talk with the authors. Okay, thank you very much.
And let's reduce a little bit. We meet again for the section 20 minutes. Okay, so break and thank you.
Hi everybody, this is Bogdan Nicolae, the first speaker. Can you hear my? Can you hear me? Can you see my slides?
Very good. Hi Bogdan.
Okay, great. So shall I proceed?
Not yet.
Not yet.
All right, Bogdan, we're going to get started, and welcome to our room back from our afternoon coffee break. I'm Brian Van Essen from Lawrence Rural National Lab. I have the pleasure of hosting our last three talks for the day on AI. Our first speaker is Bogdan Nicolae from Argonne National Laboratory. So take it away.
So thank you, Brian. First of all, I would like to acknowledge my other co-authors, Tanner Hobson from University of Knoxville, Tennessee, Orchun Ildiz, Tom Peterka from Argonne, and Dimitri Morozov from Lawrence Berkeley National Laboratory. So to begin, let me first introduce the context of our work. So we are seeing an increasing convergence of HPC and AI. On the industrial side, we see applications in a diverse set of areas: image recognition, automated translation, self-driving cars, maybe also not user-facing applications like business intelligence, data mining, knowledge extraction. So all this is powered nowadays by AI and can go much deeper than what was possible with big data analytics. And this is increasingly making use of HPC infrastructure. On the scientific side, our scientific applications were so far driven by simulations, but now we see also increasing use of AI. So, for example, individual time steps in a simulation would be accelerated by inferring the results through an AI model, which is much faster than doing the actual computations. Or we have workflows where originally we ran a simulation, interpreted the results, and then ran a next simulation. And this interpretation was done by humans. And now we can automate this by using AI. Or we have even applications that make direct use of AI. For example, at Argonne, we have a cancer research application. And this uses AI to detect tumors in medical images, or it personalizes the treatment of patients based on their genetic profile, and so on. So towards the future, we are even looking forward for self-driving laboratories where AI would drive not only simulations, but also real-life experiments using, for example, robotic arms. And all in all, AI is now the main driving force behind HPC. So one of the key challenges in AI, and in particular deep learning, which is the flavor of AI we are mostly interested in HPC, is the fact that the training is very costly, right? And so here on this chart that you may be familiar with, up until 2012, you can see that there was a relatively shallow growth of deep learning. So we had doubling of the training time every 2 years, but now since 2012, because of the accessibility to data and the growing complexity of the models, we see doubling every couple of months, right? And this trend is even growing higher, and would make training even more difficult in the future. So what exactly does the training involve? So we have an input data set, and this is split into mini batches. Mini batches obtained by sampling data from the input data set. And then we have a deep learning model that originally starts with random weights, and we have iterations that involve this mini batch. So a forward pass in which the model is predicting the output based on using the mini batch as an input. And then we adjust the parameters of the model based on the difference between the predicted output and the actual output that we expected. And if there is a difference, of course, we do these parameter updates, and we repeat this until we pass over the whole input data set. And this is what we call an epoch, and then we run multiple epochs to reinforce these patterns. So now we want to make use of HPC infrastructure to do this training at scale. And we have techniques to do that. So if the model doesn't fit in the memory of a single device or compute node, then we use model parallelism, and this involves splitting the model into groups of layers that we compute on different devices or compute nodes. And if, on the other hand, the model fits in the memory of a device or a compute node, then we use data parallelism. So we replicate each model on these devices, and then we split the data into partitions, and each worker will look at a different partition. But during the backward pass, they will average the gradients. So these differences between the expected result and the predicted result. And then all these model replicas will be synchronized. So in practice, this is a little bit more complex than doing these steps serially, because we want to make use of the high degree of parallelism that devices such as GPUs offer us. And then we have hybrid pipelines that combine data parallelism with layer-wise parallelism. So this works in the following fashion. We have the forward pass, which runs on each model replica independently. So each worker then has a different prediction. And then based on that, we start the backward pass. And in the backward pass, we have two aspects that we can run concurrently. So one is calculating the local gradients, for example, for the last layer. And then once we do that, we can calculate the local gradients for the previous layer. But in parallel, then we can proceed for that last layer specifically to average the gradients and then update the weights. And so this way we overlap a significant amount of communication due to all reduce and and these memory accesses to wait updates with, you know, the actual computations involved in the local gradient calculation. And so then the model replicas will be synchronized layer-wise. And at the end of the iteration, they will remain identical. So now let's come to the object of this paper, which is how do we provide fault tolerance for data parallel training. So if data parallel training is running at scale and is running for a long time, there is a chance that some of the workers will fail. And so the traditional way of addressing fault tolerance is through checkpoint restart. So we checkpoint periodically, and in the case of data parallel training, since the models are synchronized, only one of the replicants needs to checkpoint. So this is a little bit easier than in the case of general HPC applications, where checkpointing involves a lot of data and causes I/O bottlenecks. But still, that worker that needs to checkpoint can become a straggler and slow down the whole group. And also restart may involve high overheads because of initialization and the need to integrate the workers that replace the ones that have failed. And so we have techniques to make checkpoint restart efficient for data parallel training and deep learning in general, not just data parallel training. I could mention as a state-of-art our own previous work and other techniques from last year, check frequency that introduces asynchronous serialization and snapshotting on the GPUs. Our own work was based on the idea of augmenting the execution graph to capture different layer shards and then flash them to stable storage. So, however, the problem with these approaches is that even if we manage to get the overhead of checkpointing to zero in the ideal case, we still deal with the problem of having to recompute everything, all the progress lost from the moment of the checkpoint up to the moment when the failure happened. And then in this case, we have an opportunity to improve on this approach. And ideally, we would like to get rid of this replay overhead. So a few observations here. So not all workers will fail at once. And in that case, we have all these replicas on the compute nodes that survived, right? And if the failure happened during the forward pass, then we are in a consistent state because no wait updates were applied yet, right? So this situation is easy to address. The question now is what happens if a failure is during the backward pass? And in this case, it could be that we manage to update only a few of the layers, and other layers remain unchanged, and therefore we are in an inconsistent state. And so the question is, can we repair these partially consistent models so that we can avoid applying traditional checkpoint restart and pay for this replay overhead? And we have a trade-off here. So performance-wise, this will be very fast. But on the other hand, we may lose accuracy because we are trying to repair the state. So in this regard, we propose the two strategies that avoid traditional restart. So one of them is immediate rollback. And this works by letting the normal pipeline proceed as normal. So we have the forward pass. We calculate the local gradients. In parallel, we perform all reduce and we update the weights. But if we encounter a failure, then the survivors will initialize more workers to complete the set of workers that we need. And then they broadcast an in-memory checkpoint of the model to these new workers. And then all of them go back to the beginning of the iteration and replay the same mini batch. And in this case, then the influence of the training samples from the mini batch will not be lost. But at the same time, we will have some of the patterns in some of the layers that managed to get updated in the first phase. So this will be reinforced, right? And this will cause the potential deviations in accuracy from a failure-free run. So the other strategy that we proposed is forward recovery. And in this case, we don't initialize any spare workers to complete the group of workers that is part of the data parallel training. We simply continue with the survivors. And in this case, then we average the gradients just among the survivors. And the advantage of this is that we don't replay anything even at the level of a single mini batch. So this provides the maximum performance. But on the other hand, the influence of some of the training samples will be lost. The question is, how will this impact accuracy? So to study, the trade-off between the accuracy and performance, what we did was to provide a failure injection and simulation framework for these two strategies. And we built this on top of Keras and TensorFlow with the Horovod as the library that enabled us to do data parallel training. So we customized the optimizers that are coming with Keras by default. And we wanted to be able to study the failures, the impact of the failures and the efficiency of the two strategies at fine granularity. So then these optimizers allow the user to specify on what workers the failures would be simulated and at what point during the backward pass we would like to simulate these failures. And as mentioned, the forward failure during the forward pass is trivial to handle, so we don't study this scenario. And we don't actually kill any workers. What we do is when we reach the point when during the backward pass when a failure is desired to be simulated, we simply fill the gradients with zeros from that moment on, which means that there will be no weight updates, right? The values will remain the same, and this is similar to a failure that keeps the model in an inconsistent state. So how do we apply this to the two strategies? We have the immediate rollback, in which case all ranks have a failure simulated, and then in the second phase we replay the mini batch, but this time we don't simulate a failure anymore. And for the forward recovery, we have some ranks that suffer a failure, and then we have to change the average function to divide by the number of the survivors. So using this implementation, we ran a series of experiments, and our experimental platform at Argonne is Theta GPU. So it has 24 nodes that are quite bulky, with 8 NVIDIA GPUs and a total of 320 high bandwidth memory. We have 1 terabyte DDR4 memory on each node, and low latency, high throughput interconnect. So what kind of experiments we are looking for? In terms of compared approaches, of course, we use a traditional checkpoint restart, and then our 2 strategies. The metrics we are interested in are the runtime overhead, so the performance, and on the other hand, the accuracy. And we want to study trade-offs in this space. And in terms of applications, we look at 2 models. So one of them is the cancer research application that I mentioned in the beginning of our talk. So in particular, we look here at a benchmark called NT3. And we use also a very popular model in the AI community, ResNet-50, which is in the area of image processing. So now a key question is, since the training takes a long time, so maybe during training there will be different patterns. Then the impact of failures will be different at different moments during training. So how do we select the moment when to simulate failures, right? So for this, we studied the evolution of the accuracy and the loss for the 2 applications. And then we identified the different phases. At the beginning, for example, the accuracy grows very fast. And then towards the end of the training, the accuracy flattens out, right? So we chose then 4 representative iterations for ResNet-50 and 3 for Candle. And this is what we will call for the rest of this talk scenarios. Now, first, let's look at the traditional checkpoint restart. When we studied the checkpointing overhead in the context of run of the 2 applications on 8 GPUs, so the parameters of the model and the overheads are listed in the table on the left. We have checkpointing overheads and restart overheads in the order of seconds. And this at first sight may not seem significant, but if we want to checkpoint frequently, then these overheads will add up over a long training duration. And at the same time, even if we manage to reduce these checkpoint and restart overheads to basically 0, if we checkpoint, say, at the end of every epoch, then for the considered scenarios, we will have a significant replay overhead to catch up from the moment when we restarted up to the moment when the failure happened. And these overheads can be as high as the order of minutes. So then we studied our 2 strategies. And first, let's look at ResNet-50. These graphs represent the accuracy on the top and the duration of the iteration on the bottom. And with respect to accuracy, we have the absolute values, the height of the bars, and then the relative values to the baseline. So the run of the iteration in failure-free mode. And these are the percentages on top of the bars, right? So before represents the iteration right before the iteration that during which we simulate a failure. so the baseline, right? And we included this in the comparison because we wanted to make sure that any potential deviation of accuracy from the baseline due to our two strategies is not significantly larger than the accuracy that we had in the previous iteration. And indeed, we can confirm this. So for the two strategies, IAR represents the first strategy and FR forward recovery represents the second one. And we have also different moments during the back propagation when we simulate the failures at 25% progress, 50% progress, and 75% progress. So this is part of the levels on the x-axis. And in the case of forward recovery, in addition to these percentages, we also have a variable number of survivors, 2, 4, and 6 that we study. And as you can see, the deviation of accuracy from the baseline is very small. In many cases, it is 0 or less than 1%, 0.6. And only in the beginning of the training, so the red bar, sometimes for forward recovery, it is around 4-something%, but this is still much lower than in the iteration before the baseline, right? Where in the case of the red bar, this is 8.5%. So overall, we can conclude that the two strategies actually introduce very little accuracy loss. And in terms of performance, then if we look at the bottom chart, we can see that even in the worst case, when we replay the mini batch, we increase the duration of the iteration by at most 2x, right? So overall, the duration of the iteration is less than half a second, which is orders of magnitude less than what we saw on the previous slide for the replay overhead. And the same story repeats also for candle. So here we have 3 scenarios, so 3 bars. And again, the accuracy loss is minimal on the top chart, and on the bottom, the duration of an iteration is in the order of a few seconds. And with the forward recovery, we basically have 0 overhead. And in the case of immediate rollback, we just double this, but still it remains in the order of seconds, orders of magnitude less than if we apply checkpoint restart. So with this, then I would like to conclude, and just to remind you that we are adopting deep learning at large scale on HPC infrastructures. Data parallel training is particularly popular to achieve training scalability. We don't want to apply traditional checkpoint restart techniques because they can have a significant overhead. And instead, we propose to relax resilience strategies that introduce a minimal accuracy loss, but reduce these overheads by orders of magnitude. And so we have a failure injection and simulation framework for these two strategies, and we plan moving forward to actually provide an implementation for them and adapt it to our applications in our lab. So thank you very much.
Thank you very much. Do we have any questions from the audience for Bogdan? Okay, so I have a question. Let me see if I can get myself on camera here. Maybe, maybe not. So thank you for the talk. So I wanted to ask, I guess, a two-part question, which is, in your immediate rollback, you mentioned that you are going to bring spare resources online. And I didn't quite catch. There's a challenge is if you bring new compute resources in, don't you have to reprovision your MPI communicator for Horovod and restart the whole calculation? Or if you're having that spare resource online the whole time for additional resilience, don't you have an ongoing opportunity cost of extra resources hanging around that are not doing productive compute? Can you please address that?
That is correct. That is absolutely correct. But for the case of immediate rollback, we can also attempt to do that just with the survivors, like in the case of forward recovery, if that is a concern.
All right, but wouldn't that mean you're basically always going into the lossy forward recovery mode if you apply that approach?
So that depends on the application. In some cases, maybe the training samples may include some outliers, and then the application may not want to run the risk of ignoring the influence of those training samples, right? And then in that case, they would be willing to pay the little extra overhead of the immediate rollback, right? But in the general case, yes, probably forward recovery will make more sense.
Great. And then any other questions yet, or I have one more. So I guess the second question, I believe you addressed it, but I just want to double check, which is in your forward recovery, when you lose resources, you now no longer have the same size mini batch. And it looks like that you're scaling the effective mini batch size, the learning rate with respect to the effective mini batch size, regardless of how, or with respect to how many resources you've lost. Is that correct?
So we didn't look at this aspect in detail, but we are assuming that at the end of the mini batch, then you can bring new workers in, right? And again, you can repair the whole group of workers, right? So that you make them whole. Otherwise, yes, there are trade-offs to consider if you just continue with the survivors and you never add more spares to the group.
All right, well, thank you very much. Let's thank Bogdan again, and if our next speaker could come on up. Thank you.
Thank you.
All right, well, we're just getting started here. Our next speaker is Jasmine. He will be talking about failure identification and unstable log data using deep learning from the Technical University of Berlin in Germany. Thank you very much.
Thank you very much for the introduction. Hi, everyone. Thank you for being here to the talk. So my name is Jasmine Bogatinovsky, and in the following 20-25 minutes, I will present the paper for identification from unstable log data using deep learning. So the key idea is to detect and classify different failures based on log data. So sorry about it. Okay, so I'll start with one story. So end of January, I was writing something on Overleaf, being in the mood and being in the flow, writing. And this page pop up somehow. And I had the issue, continue obviously doing the work, and I was starting like observing what the issue can be. And I managed and stumbled upon the status overleaf service. And there, it's not probably seen nice. There is one red line, which is actually my event on 31st of January, where I had this action report where the failure was reported. It lasted like 2 hours. And in those 2 hours, I basically could have not done any work. And it was really frustrating for me as a user because there was some failure over there. And these failures are very often in systems and services. And I was continuing after that collecting more. I found more status services, and I calculated the mean and median failure time based on those reports, and these are the summary of total 69 services, where you can see that the mean and median time for failure is relatively high. So although majority of the services have like failures of duration of 20 minutes to 1 hour, but also you can see that there is quite a lot of some of them last like have mean failure time more than 20 hours, and obviously this is not something that we like, because this also can lead to high, despite user dissatisfaction, you can have a lot of huge economic losses. Recall, for example, like November 2021, like Facebook, like they had, due to some failure, like more than 60 million in loss. So one way how we can detect logs is how can detect failures is basically using logs data. So logs are actually generated from log instructions written in the source code during development, and to record some important events. And once the line is executed, we obtain the logs, and these logs serve information, can give us information that can be used for many different purposes, including like troubleshooting, control flow, system communication, and can even have legal implications, and are very important. So I will focus on, as I said, failure identification. So when we're talking about failure identification and logs, there are three ways where the failure can be, if the failure can be reflected. One way is in the semantics. So usually logs, the failures can be seen in the logs as some form of like keywords in form of success, errors, and developers and operators actually use them in order to try to detect failures. The other one is by invoke sequences, which is actually the main focus here, where we have a sequence of events, and because of some reason we can have like maybe an event will show as failure, maybe the sequence will be shortened, and that can be used in order for failure detection. And the third one is by performance anomalies, where we have a variable parameter that actually experience some abnormal value. So when analyzing sequences, we have two challenges. So when doing, we have an insufficient failure coverage. What does this mean? So during development, it's not possible, and it's not even advisable to log everything, because that brings great overhead, and there can happen that some events cannot be even logged. For example, if we have some switch, switch when it's not the cable is not well plugged, we can have a flipping interface, which is reflected in the logs as a form of repetition of the sequences. Interface change state up to down, up down, several times in short time intervals. And obviously, when observing just individual log lines, we cannot, we have insufficient failure coverage, and obviously we cannot observe the failure. And then we have the problem of unstable log sequences, which unstable log sequences is basically are normal sequences that, due to different different reasons, for example, event duplication. So because logs are usually collected at one and analyzed on one central place, we can have just some random probability of error. The logs can be duplicated. We can have error in the pre-processing technique that can also lead to errors, and then we have missing events. And the failure sequences can be quite similar to these unstable normal sequences. And yeah, this is the main challenges. These are the two main challenges. So in order to address the sequential nature of the problem, we ask ourselves, so, okay, how can we actually address the problem with sequences? So here on the slide is given a time axis. It's composed of several events. And we say, okay, can we somehow try organize these events? And let's based, for example, on this time window, and try to somehow match similar time windows. So we label these terms like sequences in some time window as subprocesses. And we will say, can we somehow extract such kind of subprocesses? What is the benefit immediately on those when we perform such representation of the subsequences is seen on this figure over here. So this figure is actually a real data. So a sequence is represented of row events from OpenStack workloads. So here on the far right, we can see that if we observe, if we calculate the entropy as a measure of uncertainty in the sequence, we can see that if we represent the whole sequence with events, we have relatively the entropy is highest, so the uncertainty is highest. Then if we observe and we represent the sequence as a sequence of windows, the entropy is a bit lower, but still those are the triangles. And if we represent the sequences with subprocesses, then we have actually a smaller number of symbols, and then the entropy is the smallest. So this is actually the main observation, how we came up with why we actually do this approach. So now the question is how to actually extract these subprocesses, and this is actually the main contribution of this work. So at the beginning, we have the raw system of messages, and we have a sequence of 3 steps. I will explain it now each and every one of them. So first, the raw of messages are parsed, parsing to extract the events. Then we have our subprocess extraction, and we have at the end our failure identifications, which actually is detecting and classifying the failures. So just briefly, for those that are not familiar, so log parsing is a procedure where we have like executed raw events, and we want to come to basically more or less to resemble the log instructions that are actually inserted in the source code. And here, obviously, we assume that we have no access to the source code. So for the first line, for example, we have VM created in 8 seconds, and its representation is VM created in notion for parameter seconds. So this is actually the what this parsing is doing, and we used the drain as a state-of-the-art parsing method. And now I will explain how we actually extract subprocesses. So the name, the CLOC, means is the name of the method that is doing the process extraction. Is composed of 3 parts: preprocessing, neural network module, and subprocess extraction. The preprocessing, so at the input we are given this sequence of events for one time window, and the preprocessing composed of 2 parts. One is the padding, which allows us, because in one time interval we can have a different number of events. In order to train a neural network, we need to unify this length. And if you notice, there is one special token at the beginning. It's called log subprocess embedding, and we are using this token in order to later running process to extract learnable representation of the event. And then we have the procedure of masking, and this